home in Oak Ridge, Tennessee. And I guess for the next 50 minutes or so, we'll take a look at high performance computing and some of the challenges that face us in the future with the use of these machines. So just as an outline, I'm going to look at high performance computing in general, look at where we've been and where we're going in terms of the direction, and look at some of the issues that we have facing us in terms of the use of these machines. And we're going to look at some examples in linear algebra, since that's really what I do. Okay, so high performance computing really covers a very broad and diverse area of applications. They're critical for many science and engineering applications. Some of these occur, of course, in research laboratories, but many also occur in industry. And we'll see just how important they are in industry as we move on. But things like aircraft wing design, noise reduction, computational materials, deep learning, and data mining all have applications steeped in high performance computing. You know, the thing that touches us every day with high performance computing and supercomputers is the weather. So the weather is forecast both near short-term and long-term in terms of high-performance computing, the use of high-performance computing to do those forecasts. Sometimes they get it pretty well. They get it pretty good. Sometimes they have a hard time getting it. Sometimes the forecasts are not so good. So you wonder what happens there on Friday with the temperature, and maybe a catastrophe occurs on Saturday. We want to take a look at the fastest computers. We want to take a look at, look at some of the features of them. These are important machines. They provide strategic importance in terms of scientific discovery, in terms of looking at national security. They really contribute to the economy and industry, making those industries more competitive. So today, supercomputers are tools for solving some of the most challenging problems through the use of computational simulation. We're going to take a look at these computers through the eyes of some data that we've collected. This is some benchmark data, and that data goes by the name of the top 500. So this is a list of the 500 fastest computers. This list comes out twice a year. It comes out in June and also in November at the big supercomputing meeting in the States. This year it's held in Austin, Texas, and in the summer it comes out at the German meeting, which will be held in Frankfurt this next year. And this benchmark looks at solving a mathematical problem, numerical problem, and you want to solve this problem here. It's a linear system of equations, AX equals B. And we're going to solve a dense matrix problem. And you're going to solve that problem for this benchmark using a very standard method. You must use the algorithm, which goes by the name of Gaussian elimination with partial pivoting. So that's a standard method. You probably learned it in high school. And that's the method that we're going to use to solve the problem. You get to implement that as best you can on your computer. And the idea is that you would fill up your computer with a matrix. I'm going to give you the matrix. You're going to solve it using this very fast implementation of that method. And then we're going to measure the time, and we're going to change that. We're going to convert that time into a rate of execution. So we're going to look at the rate of execution that you solve this problem. And typically what happens is as you increase the size of the matrix, the rate of execution goes up until you reach some asymptotic point. And that's really what we're trying to capture for your machine, this asymptotic point. Okay, so this graph presents, in some sense, a snapshot of high-performance computing over the last 23 years. It's a graph of the top 500 list. The red line there is charting the #1 computer. So back here in 1994, the fastest computer, this dot represents the fastest computer, and it was running at 60 gigaflops. So that's 60 billion floating point operations per second. And the floating point operations we're talking about here are all 64-bit operations. And you could see today, the fastest computer today is a computer which is running here at I can't quite see it because I got this other thing in front of it. There it is. It's running at 33.9 petaflops, and the blue line is representing the lowest computer number 500 on this list, and it's at 166 teraflops today. So the fastest is at 34 petaflops. That's 34 times 10 to the 15 floating point operations per second. The lowest one on the list today is 166 teraflops, and that sort of gives you the spread, if you will, from high-performance computing. Notice that the number one computer has been the same for the past 5 lists. So the first time it came out, it had the number one machine hasn't changed, and that's a little unusual in terms of the list itself. You can take a look back and see that that's only happened once before. And I would anticipate that machine that's number one is going to be number one for a few more times. And we'll take a look at that also. The orange line is charting the sum of the 500 computers. So that's at 362 petaflops today, or a third of a exaflop. That's an Excel sheet computation. That's just adding up the 500 computers and looking at the list. There's a number of interesting things that come out of the list. The slope of the line. So the slope of the line there, you might think, behaves sort of like Moore's law. Well, it turns out it's, in Moore's law, it says something's going to double every 18 months. So it turns out that the slope of the line here is doubling every 14 months. And you might wonder, why is it doubling every 14 months? And it has to do with the use of parallel processing. So every time this list comes out, we're deploying more and more processors in each of the machines, and that sort of gives this boost to what we would call Moore's law. The machine at the bottom of the list today, it's sort of stunning. This exponential effect that was equal to the sum of all 500 machines back in 2001. The other thing that's sort of incredible in my mind is I'm giving this talk on a laptop, and that laptop, I can run the benchmark on it. And when I run the benchmark on my laptop, it's a dual core Intel processor. I get 70 gigaflops out of my laptop. And that's a stunning achievement for a device that I can run for probably 12 hours on a battery and use on an airplane. And, I mainly use this machine to read email and give talks, to be honest. And here I've got a device which is 70 gigaflops. And when we look at that performance, that's faster than the number one machine back in 1993. That number one machine in 1993 was a thinking machine, CM5, with 1,000 processors in it. So it's incredible changes have taken place in really quite a short period of time. And not only do we see that in our regular computers, but even in the devices that almost everybody carries with them. So my iPhone, has a few processors in it, and you can run the Linpack benchmark on your phone. There's an app for that. You can download it, and when you run the benchmark on your phone, you get 4 gigaflops out of it. 4 gigaflops. That's an incredible rate of execution for a device that we carry on our belt. And not too long ago, that would have been one of the fastest computers on the list. So very striking changes taking place in really quite a short period of time have given us devices which are just amazing in terms of the computational power. If you stare at this list, you'll notice that there's sort of a kink that's occurred in the list at the bottom of the list here. So there's been a fairly straight behavior that's taken place, and the extrapolation isn't going to be quite true if we take it forward. There's been a kink that's occurred, and that kink is mainly the result of a lack of investment in high-performance computing. So when we look at the number of computers, the new computers that have come on the scene, we see that that rate is really much lower than it has been in the past. So the investment, maybe it's an economic reason, has not been there for the replacing computers, let's say, on this list of the fastest machines. And it'd be interesting to see how that evolves in the near future. So that's that effect I've just mentioned there with the machines and things changing. So if we take a look at the state of supercomputing today, what we see is that today we have petaflop computers. There are 67 machines which have petaflop computing, or systems which have greater than 10 to the 15 operations per second. We see basically three technologies that are appearing as architectures for the future. And the first architectural line is based just purely on commodity processors. And by that I mean Intel processors as a typical commodity processor. So people are building large machines. They're being integrated using Intel processors together with some commodity interconnect like InfiniBand. The second technology lane that we see deployed is using commodity processors again, but with some kind of accelerator. And the accelerator would be something like a GPU, or Intel calls them coprocessors. And today there are 88 of the 500 computers which use this hybrid kind of approach to high-performance computing. And the third swim lane, I'll say, is something which uses or deploys special-purpose lightweight cores. And an example of that is the cores that are in the IBM Blue Gene, although IBM is no longer making Blue Gene processors, or what Intel has in its Knights Landing processor. So Knights Landing is the next generation of Intel's coprocessor, very lightweight cores that one can actually build a system out of, not think of them as an accelerator, but think of actually building the system out of these components as being the hosted part of the computer. And another example of lightweight cores would be ARM processors. And we're starting to see ARM processing appear in high-performance computing as well. Today, we see an increased interest in high-performance computing worldwide. We see high-performance computing being deployed in the US, in Europe, in Japan, in China. One thing that's sort of interesting here is over 50% of the 500 computers, the 500 fastest computers, are in industry. So industry sort of gets it. They understand that these high-performance computers can provide some kind of strategic advantage for their business, something that gives them a competitive edge over others in the field. And those computers, those 50% of the computers, are really towards the low end of the 500 computers. That is, they're not at the very top end of the list, but they're still being deployed in an industrial setting. And the final thing I'll comment on is Intel. They really have the largest share. So if we look at the machines out there, 86% of the 500 computers use Intel processors to do their computing. And there's another 4% that come from AMD. So x86 architecture is something which is in 90% of the high-performance computers today. And that's a stunning statement that commodity processors really has driven high-performance computing today. And that's not the way it was, let's say, 10 or 15 years ago, when we had very special purpose scientific computers that were designed specifically for large-scale scientific computing. Today, the market has shifted over to a commodity processor. Commodity processors have matured to the point where they do provide reasonably high performance rates, and because of the sheer numbers of them, the price per unit is relatively low. If we take a look at the top 10 machines, this is what we see. So the way to read this here is this is the #1 computer, and it's at the National Supercomputing Center in Guangzhou. That's a Chinese machine. It's called the Tianhe 2. It was built by the National University for Defense Technology. So this is a university in China which has been involved in high-performance computers for many, many years. They've designed and integrated systems over a long period of time. This particular machine uses Intel parts. It uses a 12-core Xeon processor, plus Intel's coprocessor, the Xeon Phi. And the Chinese have built their own custom interconnect. So NUDT has designed and implemented interconnect, which has slightly better characteristics than InfiniBand, and that's how data is passed along around through this machine. The stunning thing about this computer is it has 3 million cores in it. So 3 million cores. And if you think about using this machine, each of those cores, you really need, if you're going to drive it at high performance, at the peak performance, you need 4 threads of execution per core. So if you're responsible for programming this system and you're going to run one application on it, and that's what they do at certain times, then you have to sort of think about maintaining 12 million threads of execution in order to effectively sustain a computation at this, on this device. The performance for the benchmark was about 34 petaflops, so that's the #1 machine, and that's 62% of the theoretical peak performance for this system. So the theoretical peak is a paper and pencil calculation. You look at the cores that are in the machine, you look at the cycle time, you look at the number of operations you can complete per cycle, and that'll give you a measure of the theoretical peak. And then you run a benchmark like this benchmark, and then you look at the difference. And in this case, they've achieved 62% of that theoretical peak. This machine uses about close to 18 megawatts of power. So 18 megawatts under load is what this system is consuming. So in the US, I'm not sure what it is in Australia, but in the US, a megawatt year is about $1 million US. So this machine, to turn it on, if it was in the US, would be about $18 million to run it for a year. That's just the power that's needed for the machine. The machine itself cost on the order of roughly $500 million US to run this machine. So it's a very, very big expense. Most of the machines at the top of the list go for around $200 million or above, as you see in this machine. And again, power is a big deal with these machines, as is the cost. The last column here represents an efficiency. So this is the flops per watt. So you want this number to be as high as possible. So in this case, we have about 2 gigaflops per watt. So that's sort of the standard for these kind of machines. And if we go down the list, the #2 machine is at my lab, Oak Ridge National Lab. It's a machine made by Cray. It has AMD processors with a Kepler accelerator. It uses a custom interconnect that Cray has designed. This machine has about 500,000 cores in it. And notice that the performance that it achieved is about half of the performance of the Chinese machine. In fact, the #2 and 3 machine on the list is just a little bit more, when you add them together, is a little bit more than that #1 machine. So #1 machine is very powerful in terms of what it can do. If you scan down this list here of the top 10, you see China, US, Japan, Switzerland, Germany, and Saudi Arabia rounding out the list. The list of the top 10 machines has been pretty static over the last 3 years, I'll say. Occasionally we get a new machine being injected, one new machine in the list. So Kaust, this machine in Saudi Arabia, is was the new entry this last time. So that's a machine that was made by Cray. It has Intel processors, and it has Cray's custom interconnect, and about 200,000 cores in that machine, achieving about 5.5 petaflops of execution. So just scanning down the list, one thing we note is the number of cores in this system, large numbers of cores. We got 3 million in the #1 machine. There's another machine with the 1.5 million cores in it, but all of these machines have hundreds of thousands of cores in them. And when you buy a machine like this, you're intending to use it at scale. That is, you're intending to run some applications at scale. You're probably not going to waste the machine in terms of running thousands of jobs simultaneously on it. You're going to be running, the intent is to run large scale problems on these systems. The other thing that we notice is that power is a big deal. All of these machines consume over a megawatt of power. The lowest one is about 2 megawatts of power, and the largest one again is about 18 megawatts of power. The other thing to note is that 4 of the top 10 machines use accelerators. So accelerators from Intel or from NVIDIA that are used to boost the computation above what we can get out of commodity processors. In fact, the 3 architectural lines are represented here. Straight commodity processors that we would see, say, out of the machine that comes from Kaust, or even this machine, the K computer. Then we have hybrid systems, these 4 machines that use accelerators. And then we have a few machines which use very lightweight cores in the form of the Blue Gene. 4 of the systems on the top 10 list use that core as its base processor. If you're interested in Australia, Australia has 7 machines in the top 500, and I've listed them here. It's got a machine at position number 15. It's at Tulip Trading. I'm not exactly sure what Tulip Trading does, but probably does some sort of commodity trading. They're using a high-performance machine, perhaps to do that kind of arbitrage or looking at futures for the market. And then there's more traditional high-performance computers here at various places, ANU, CSIRO, and a number of other research places in Australia. You know, we have these 88 systems which use accelerators, and I just want to tell a bit of a story about accelerators. Since they do play an important part in boosting performance, they get their boost by taking a commodity processor and putting this accelerator next to it. And the way this works is the commodity processor's in charge. In this cartoon, there are eight cores in this Intel Xeon processor. It has the 8 cores plus some memory associated with it. And then there's an accelerator which is attached. The attachment comes about through the memory. So there's a DMA connection which is realized by a PCI Express bus, which allows you to pass data from the host memory over to the accelerator memory. So you would think about passing information over to the accelerator. The host program then tells the accelerator to do something, to run a program that executes with the memory that was placed over on the accelerator. So it does some operation over here on the accelerator. In the meantime, the host processor can go off and do something asynchronously. So it can do something and later check to see, in fact, if the data is ready, finished, if the computation is finished on the accelerator, and then drag the data across this link here between these 2 memories. The thing to note here is that the memory speed on this machine is measured at 1 gigaword per second. The word is 64 bits in this case. And the performance that it's capable of is about 1.3 teraflops. So there's roughly 3 orders of magnitude difference between the flop rate and the bandwidth that we can move data. And remember, you have to pass data over to this device to do the computation. So in order to fully use this floating point rate here of a teraflop, you need to pass data and get a lot of reuse of the data. That is, use the data over and over again in order to effectively pay for the cost of moving the data over that very slow link before you have to pass the answer back. So that's going to be sort of an issue with accelerators. Is can you, in fact, overcome that very slow data transfer in terms of getting reuse out of the data once you have it over on the accelerator. And of course, we're not interested in one accelerator on a board. What we typically think of having multiple sockets on a board, and then we put multiple GPUs on that board as well, trying to squeeze as much computing power as possible out of that space and effectively trying to spread the computation across that. And that presents some real challenges for a program to effectively exploit that power and effectively balance the data movement across those links. Some recent developments, the U.S. Department of Energy is planning to deploy a number of systems which are on the order of 100 petaflops, and that'll be sometime in 2017 and 2018. They're going to invest about $500 million in the hardware. There'll be another $500 million invested in the software and algorithms that will be needed to run on those systems. So they're planning on 3 systems. They're planning on a system at Oak Ridge National Laboratory, one at Lawrence Livermore National Laboratory, and one at Argonne National Laboratory. The Oak Ridge and the Livermore machine will be based on a design from IBM and NVIDIA. So they're going to use an accelerator from NVIDIA, and they're going to use a processor from IBM. In this case, it'll be the Power 9 architecture together with NVIDIA's future generation accelerator. At Argonne, they're planning to base the system on Intel's products. So Intel has a roadmap for their coprocessor, which basically takes the coprocessor and has it self-hosted. So there's not going to be that front-end issue about moving data back and forth. And it'll be the next generation beyond what's planned this year. So it's a couple generations future. It goes by the name of Knight's Hill today. And those machines will be on the order of a few hundred petaflops. And that is the stepping stone to exaflop computing. That's the current thought. So the next crank of this of these architectures would bring exascale computing 10 to the 18 floating point operations per second. One of the other things that's happened is the U.S. Department of Commerce is preventing China, certain groups in China, I'll say, from receiving Intel technology. So China has been taking Intel parts and integrating them into large systems. So what they've done recently is the U.S. Department of Commerce has cited concerns about nuclear weapons research being done on the Chinese systems. And they basically have denied access to the technology to 4 centers in China. So the National Supercomputing Center in Guangzhou, that's the site of the #1 computer, the Tianhe 2. The National Supercomputing Center in Tianjin, they have a very fast computer, which is the previous generation of the #1 system. They're preventing the National University for Defense Technology, which are the integrators or the developers of these systems, from acquiring Intel parts. And then also the National Supercomputing Center in Chenchaa, where the National University for Defense Technology is located. So, China was planning to deploy 100 petaflop systems at the end of this year based on Intel technology, and that plan is now stopped because of this embargo by the Commerce Department over Intel technology. And one of the issues here is we've reached a point where the U.S. has less than half of the 500 fastest computers. That's the first time that has happened, and we see China with a country with the 3rd most number of these high-performance systems, about 37 of these high-performance systems. There was a meeting in Germany, this international supercomputing meeting, and there was a talk given by Yutong Liu, who's the software architect from the National University for Defense Technology. And she said that in light of this embargo, the Chinese are going to develop their own accelerator, not use Intel's accelerator, in the next generation system. So Intel is used currently in this machine called the Tianhe 2, and that's this machine which has a peak performance of 54 petaflops and has certain characteristics associated with it using Intel processors. But the next generation is going to be based on this computer. They're going to expand it slightly, and they're going to replace the Xeon Phi coprocessor with a Chinese accelerator. And that will boost the performance up to the point of reaching this 100 petaflop threshold. There's also statements about a second machine being developed in China based on a Chinese processor, the Shenwei processor. So the accelerator that China is developing is reported to have these kind of characteristics. So again, it'll be Intel Xeon processor together with this Chinese accelerator. The Chinese accelerator has about 2.4 teraflops of double precision performance, has fairly high memory bandwidth, and fairly large memory associated with the accelerator. It still suffers from this very weak link between the floating point part and between the host part and the accelerator part, and that's something we have to live with, at least for the current time. Well, you know about Moore's Law. Gordon Moore, back in 1965, made this conjecture about the number of devices on a chip doubling every 18 months, and that was based on 5 points that he had in his paper that was deriving this conjecture. And that's held for a number of years. So we've seen the number of transistors doubling at that rate in new processors, doubling roughly every 18 months. An incredible path we're on. My architect friends tell me that Moore's Law is not quite over yet. It's going to continue for at least a few more years. So we'll continue to see this increase in the number of transistors. But the real secret sauce with Moore's Law is not the number of transistors. It's this thing called Dennard scaling. So Dennard scaling has been, Robert Dennard was a researcher at IBM, and he came up with his colleagues with this conjecture, not conjecture, but the way things work for semiconductors. Basically, you can decrease the feature size by some factor. You could decrease the voltage by that factor, and you could think about increasing the number of transistors by that factor squared, basically the area squared. So you're going to be able to decrease the feature size, decrease the voltage, and have an increased number of transistors. And that allows you to increase the clock speed by that factor. So Dennard scaling puts those transistors to very good use. It says when the next generation of your machine comes out, you get this alpha factor of scaling that occurs. And that gives you a boost in terms of the transistors, but also it gives you a boost in terms of the clock speed. So the energy consumption doesn't change under this. So it's an incredible situation. Increased transistors, increased clock speed with no additional energy consumption. So we're doubling the number of transistors, say, we get a 40% faster device, which is 50% more efficient. So that's Dennard scaling, and that's an effect that's been in place for a number of years. However, unfortunately, Dennard scaling is over. So the breakdown with Dennard scaling has resulted because of the small feature size. There's this increased current leakage that's occurred, and that current leakage leads to heating up the chip. So the chip gets too hot, and you can't run a chip given those characteristics. So today we had to cap the cycle time of our chips basically at roughly 3 gigahertz, and that caps the power consumption of the processors roughly at 130 watts. So powering the transistors without melting the chip has really been an issue, and unfortunately Dennard scaling is over. But Dennard scaling with Moore's law has been the big deal over recently, and now that Dennard scaling is over, those transistors are being put to use in terms of giving us additional processing capability. So the clock cycle time is basically stuck because of Dennard scaling. Those additional transistors are being put to use in terms of giving us more computing power on the chip through a multi-core device. So roughly in 2004, when Dennard scaling broke down, multi-core became the model. And today, all of our systems are based on multi-core technology. All the processors that we have from Intel, from IBM, from AMD, from NVIDIA, from Fujitsu, and Shenwei, the Chinese company, all use multi-core technology. One of the problems with the processors that we have today with multi-core is we're increasing the computational potential of this chip by these additional processors that we have. But the data has to get into the chip some way, and the data gets in on the pins at the perimeter of this chip. So we're increasing the amount of computing power on the chip. So this area is increasing the computing power, but the perimeter is not going up by that same kind of factor. So that leads to an issue about getting data into the chip, into the processor, so it can effectively use the computing power there. One of the issues in the future is we're going to go to a more integrated chip design, which has three-dimensional stacking associated with it, and also a photonic network. So instead of copper, they'll be passing information around through some kind of optic paths on the chip, and then there's this three-dimensional stacking that'll occur on the device itself. So there'll be a piece of silicon which has the CPU, the multi-core part of this thing, together with stacked memory, so information can flow vertically through that stack at a much higher rate than we can trying to get the information through the pins of this device. And that'll allow us to more effectively use the computing power that's on that device, not really being strangled as much as we are today with the data movement issue. If we take a look at what's happened in our processors, we get this interesting story. So this is looking at Intel's Xeon processor line. So in the early days, Intel had Xeon processors, and they produced 2 floating point operations per cycle. So each core was capable of 2 floating point operations per cycle. That's in double precision. The Nehalem processor in 2009 and the Westmere processor doubled that. So we were able to get 4 floating point operations, finishing every cycle in double precision. When the next generation of that chip came out, Sandy Bridge and Ivy Bridge, that doubled the floating point execution rate again. So each core was capable of delivering 8 floating point operations per cycle. Haswell and Broadwell, the processors that we have today, the processor that's in my laptop, gives me 16 floating point operations per cycle. So an incredible floating point rate for these chips. And that's the same for the coprocessor, this Intel Xeon Phi coprocessor. Each core there also gives me 16 floating point operations per cycle. So we have this incredible floating point rate that's there, but we really haven't done much to enhance the data movement part. And this is going to continue next year with Skylark at the end of this year, I guess, if it comes out, 32 floating point operations per cycle. So we get incredible floating point execution rates, but things are really starved in terms of getting the data to the processor. So if we take a look at how long it takes to get the data to the processor on our chips today, the main memory bus that we have runs at a certain rate, and that rate says that we can, if we're gonna read something from DRAM, it takes 167 cycles from the time we issue the read until the time that information appears in the cache of the machine. 167 cycles. And in that 167 cycles that we were waiting for that data, we could have done 2,672 floating point operations. So again, we have this tremendous mismatch between data movement and the floating point rate of our chips. So our machines today are really over-provisioned for floating point, and they're starved in terms of getting the information to the processor. And that's going to lead to a number of issues. In the time I have remaining, which is about 10 minutes, I'd like to go through an example here. So this is an example of my laptop. So my laptop is it's a dual-core Intel processor. Each core of my processor is rated at 2.3 gigahertz. So that's claimed to be the cycle time. But Intel has something called turbo boost. So if the conditions are right, it can raise the cycle time of the chip. I don't have to do anything. This happens automatically. In fact, I can't control it in some sense. The cycle time will just raise to 3.5 gigahertz. So the conditions are right, so it doesn't overheat the chip, basically. And at 3.5 gigahertz, something that I actually can realize, that core of my laptop can run at 56 gigaflops. So each core can run at 56 gigaflops. So my laptop is characterized by this this processor. It has some cache, 6 megabytes of cache, and then it has some memory. In my case, it has 8 gigabytes of main memory. And in order to get the data from memory to the cache, there's a bus, and that bus is rated at 25.6 gigabytes per second. So that's the rate at which I can move the data from memory into the cache. And what I want to do is to look at some very basic operations. So here's some vector operations. We're going to do a dot product or an AXP. So we're going to take a vector, multiply it component-wise by another vector, and then sum up the elements. So if the vector is of length n, I have to do 2n operations to complete that. That's a very standard, simple vector operation. So I'm going to take these vectors to be very long. What I want to do is to fill up cache and look at the performance. So I've got 2 vectors, and each of those vectors are going to be of size 375,000. So I make those vectors of that size so it fills up cache. I want to sort of downplay the latency issues associated with the example. So I make them of that size so it fills up cache exactly. Each of those vectors consume 3 megabytes of data. So my 2 vectors fit into the 6 megabytes of cache. So the time it takes to move those vectors into cache, I can measure. It's 6 megabytes of data. And I got 25.6 gigabytes per second. So it says that in order to move the data, it takes 0.23 milliseconds. In order to do the floating point operations, I'm going to do 2n floating point operations at a certain rate, 56 gigaflops. So the floating point operation time takes 0.01 milliseconds. So the floating point execution rate is insignificant compared to the transfer rate for these things. So we can think about overlapping those, if you will, and the transfer time is the thing which takes the most time. So I have a processor which has a peak performance of 56 gigaflops, and my inner product, my dot product, is going to run at 3.2 gigaflops. So I'm very disappointed with my performance if I'm going to be doing a dot product on my laptop. I'm only going to be realizing less than a tenth of the performance that it's capable of. So this kind of operation is really communication bound. There's no reuse of data going on in this particular situation. The data is read in, the operation is done, and I don't get any additional operations out of that data by doing it. We know that we have vector operations. We have things called matrix vector and matrix matrix operations. I want to take a look at matrix times a vector. And again, I'm going to size these things so they fill up my cache precisely. So in this case, I have a matrix of size 860 that leads to a matrix and two vectors consuming that 6 megabytes of data. So again, the time to move that data remains the same. It's 6 megabytes of data, and I've got a rate of 25.6 gigabytes. So it says it takes 0.23 milliseconds to do the data movement. And then to do the matrix vector product, I've got two n squared floating point operations, and that's going to go at 56 gigaflops. So that's going to take 0.26 milliseconds. So now I'm consuming more time doing the floating point operations. They're roughly the same as the data movement. So again, if we try to look at what we're going to get in terms of the performance, it says for this particular operation at 0.26 milliseconds, we can achieve about 5.6 gigaflops. So just slightly faster than our dot product, much less than the theoretical peak performance. So even this operation, doing a matrix vector operation, there's very little reuse of data. The reuse comes about just because of those vectors. So again, very little reuse. If I think about doing a matrix matrix operation, we've got two matrices multiplied together. In this particular case, I'm going to size them again to fill up my cache exactly. So the time to move the information remains the same. And now the time to do the operations looks like something 2n cubed floating point operations. And I have a rate at which I'm going to do those floating point operations. And that says to do those 2n cubed floating point operations, it's going to take 4.46 milliseconds. So now that leads to a situation where the floating point execution time is really dominating. And the model here says that the performance for that matrix vector multiply can be as high as 53.3 gigaflops. So here's a case where I'm getting very good reuse of data. I've got a problem where I have n squared pieces of data and n cubed floating point operations. I get the surface to volume effect, and I have something which can effectively use the execution speed of that particular processor. And that's exactly what we see. So we're getting roughly 95%. If we take a look at the performance that I actually achieve, that actually do the experiments on my laptop, I see this blue line here is charting the vector operations that I'm doing, 1.6 gigaflops. The green line is charting a matrix vector product at 3.4. That's what we achieve for a matrix vector product. And the red line is charting the matrix multiply, in this case, getting roughly 54 gigaflops in terms of the execution rate. And that has a tremendous impact in terms of algorithms. I've been designing linear algebra algorithms for many years. We started out using doing things in terms of vector operations, and those vector operations we thought would run well on vector computers. Well, today those vector operations suffer from the same observation we saw when we were doing vector operations on our system. We get very poor performance. We get performance which looks under 10% of the theoretical peak performance for our systems. More recently, we've changed the design of those algorithms to be block-based, where we can exploit the matrix characteristics for those algorithms. And in this case, we can realize much higher levels of performance when we're running on these cache-based systems, or multi-core systems, small numbers of cores on a system. These particular implementations run very well indeed. However, when we go to many, many processors, when we're talking about hundreds of thousands or millions of cores in our systems, we have to come about a different strategy. That loop level parallelism effectively will kill the overall effects of our computation. In our models that we have today, it's basically a loop level driven kind of algorithm. We go through a phase of the algorithm where we do something sequential, and then we branch out and do a bunch of things in parallel, and then we join back together again doing things sequentially. And that's something you can't tolerate with hundreds of thousands or millions of cores or threads of execution. That bulk synchronous processing really doesn't cut it. So we have to think about exploiting things a little bit differently. This is a cartoon here showing how that bulk synchronous processing works. This is on a 16-core system. If we look over time, how we effectively are using the cores for that particular algorithm. There are places where we can exploit the parallelism of all the cores, but then there are places where just one thing executes. So we end up with a lot of white space, if you will, in the performance graph for this particular algorithm. And what we'd like to do is to squeeze that out. And one way of doing that is, instead of just doing the first step, try to get as much ahead of the computation as possible. Try to do some of the second step while you're doing the first step. So as soon as possible, do the second step as soon as you've finished working on the data that could allow you to start the second step. And again, do that while you're still doing the first step, get as far ahead as possible in terms of going to the next step and so forth. And that leads to an algorithm which is very much a data flow driven kind of algorithm. That algorithm leads to a task-based approach to things, where you're exploiting the data flow nature of the computation, leading to a directed acyclic graph, a representation for the algorithm. So our algorithms today are being defined in terms of that data flow graph, in terms of driving the computation through a directed acyclic graph, trying to be as asynchronous as possible, still respecting the data dependencies of the overall computation. So that's basically where we are in terms of our overall computation, and that leads to very efficient implementations. Today we're using OpenMP in terms of our shared memory implementations. We define tasks in terms of these pragmas. The scheduling system with OpenMP effectively can schedule the computation across the tasks, and leading to a much more condensed execution graph where we execute that directed acyclic graph, trying to exploit as much parallelism as possible, trying to effectively execute the critical path in that graph, which would release the most layers of parallelism, leading to a very fast execution time. It looks like I have just a few minutes left. What I'd like to do is to jump ahead here and look at, give some conclusions, I guess. So I'm going to skip over this graph, this chart here. There's many frameworks which do what I'm talking about in terms of task-based systems. There are a number of designs which people are exploiting. We have something called Parsec, but our colleagues at other places are using similar ideas today. It's something which its time has come in terms of expressing algorithms in terms of this model, and I look to this as being one way to effectively exploit large numbers of processors. So here, let me just conclude by looking at what I feel are critical issues as we move forward to exascale and petascale computing. The first thing is try to have algorithms which reduce synchronization. You've got to break that fork join model of computation, that bulk synchronous processing. Look to ways of trying to avoid that, asynchronous kind of algorithms, out of order execution, those kind of things. We want to reduce the amount of communication. Today, a bottleneck is around moving data. We want to be able to come up with algorithms which have a lower bound on communication, realize those algorithms in terms of the implementations that we have. And that way we can effectively drive these algorithms at the highest performance. We want to try to use mixed precision. We want to try to use single precision 32-bit arithmetic mixed together with 64-bit arithmetic. That is, you want to maybe start the computation using short precision, and as the computation proceeds towards its conclusion, switch to 64-bit arithmetic, effectively exploiting the precision that you get and allowing you to gain access to that fast execution with 32-bit arithmetic. It's twice as fast in terms of the number of operations you can do, and it's also moving half as much data around. You have to be able to auto-tune your program. So this is a critical situation. Today, these machines are very complicated, and we can't expect the user to be adjusting dials and knobs on the software. We have to build into the software the ability to adjust to a dynamic nature that these programs are running under. So allow the software to effectively exploit that dynamic nature in terms of changing the cycle time, expanding or contracting the number of cores that are available, the number of accelerators perhaps that are with us. That has to all be done under program control, not under user control. You have to build algorithms which are resilient to faults. We have machines which have literally millions of cores in them, and things are going to fail. So we have to be able to transition past failure. Today, our programming model is one which can't do that. Our programming model is MPI. There's no fault model within MPI today. We're working on it, but we don't have it today. And we need to design algorithms which can effectively do that. And the final thing I'll just, operations. I can't guarantee how those reduction operations are going to occur on a parallel computer. And as a result, we may get things occurring in different orders that may lead to different round-off error, and that will lead to perhaps different results. Okay, so we have major challenges ahead. We have parallelism, which is growing. We have issues in terms of expressing our programs. We have this notion of hybrid programming, which leads to, again, many issues in terms of developing applications that can fully exploit the potential. Fault tolerance is going to be a big deal in the future. And this issue about the power consumption is really a first-class citizen in terms of the design and use of our machines. And it's really an exciting time to be involved in high-performance computing. There are many challenges ahead for us and many research issues that have to be explored in order to overcome the challenges that we have. So let me conclude there, and thank you for your attention. And if there's time, I'd be happy to answer any questions.